I think most or all of you know Laura Pan. She's been at NCAR ACOM since 1992. She was a high school teacher in China before she got her PhD. Got her PhD in quantum optics at Johns Hopkins and did a postdoc at NIST in quantum optics before coming here. And she's now a senior scientist here at ACOM, and she's going to talk about the ATTREX mission.
Thank you, Mike. So about 2 months ago, we started this new thing in ACOM called a weekly update. In that first weekly update, I read from the beginning to the end that there's a message that says seminar coordinators want to invite everyone, a volunteer, to give a seminar on Monday. So that day I foolishly volunteered. I thought that the whole summer will be throughout, everybody in the ACOM will be talking every Monday. You know, here's where we are talking. So this talk really meant to, I want to motivate myself to understand all the background information for the 2 papers I'm writing this summer. That's also why I want to talk about this. So these 2 papers are what I thought I owe Eric Jensen for being part of the ATTREX mission. A lot of new observations, motivated data analysis. So I have my co-authors down there from both NOAA and the NASA. And the first paper right now is in the stage of ready to be submitted, pretty close. And the second one is in the stage of drafting. And so a lot of information I added for connecting ACOM people in case you're not familiar with the TTL research. So the 1/3 of that is motivation. So I want to start from this workshop. 2001, I attended the Spark Tropopause workshop in Bartels, Germany, and that kind of the beginning of my UTLS career. I don't know how clear that is, Andrew. He's, as usual, still front and center right here. And this is myself, a younger version, and many people you might recognize, you know, Jim Houghton and Baron and Lenny Pfister and so on. So anyway, but the most memorable part of the workshop is a dialogue. It's a conversation talking about the tropopause definition. Okay, here, I'm motivating why definition is important. So this is slightly, tiny bit dramatized version, but it's close. So you can view this dynamist as an alias for Peter Hans. How many people know who Peter Hans is in this room? So anyway, so asking, you know, how we kind of understand the importance of chemistry in troposphere and stratosphere. And of course, these chemists, you can view this as alias for Ravi Shankar. So I think many of you know Ravi. So of course, they, you know, how important is the troposphere ozone? And Ravi said, you know, tell me where the tropopause is, I will answer you. And then Peter Hans will say, sorry, I should say the dynamist should say, sorry, I forgot this recording. I need to watch what I say. So being too formal, I didn't expect to be like this. You know, do you want, what do you like? Do you like dynamic tropopause? Do you like thermal tropopause? Of course, the question is, which one is the right one, right? So this is a, really was an interesting motivation for me to realize, you know, now you know I'm trained as a physicist and working in the chemistry division. Very often I feel motivated to connect the information in the dynamics to the understanding of composition. And after this work, I hope I'll convince you the information in the chemical composition will provide a very strong piece of insight into dynamics and circulation. So
the chemists aren't really capable of understanding.
yeah, you're a minority. You can get it. So anyway, so this is a textbook version of the picture. I want to start from somewhere everybody would agree or consent and understand. That is, we have these two layers that is so interestingly close to each other. That is, you have this very fast overturning layer called the troposphere. And then immediately you have a layer above, and it's a strongly stratified, meaning move vertically very slowly and very fast horizontally. And the transition between the two is this thing and discovered more than 100 years ago called the tropopause, where the turning stops. Then the question is, how do we expect the tropopause to behave or the change to behave, right? So this is a very nice paper by Ed Danielson and his student, and I think used to be Eric Jensen's boss at Ames. So we can expect the transition to be sharp. That is called the zeroth order discontinuity, but it's rare. And very often we have to expect there's a transition to be in first order, second order, so on and so forth. So what is this quantity? He mostly emphasized the PV and the static stability, which is a gradient of potential temperature. And later on, I want to show there are many other quantities also show discontinuity. So I want to focus on tropics today. The tropics, there's two definitions in most often that being used. One is what we call the lab street tropopause. The other is a cold point tropopause. You will hear this throughout my talk, LRT and CPT, so it's important to remember that. So this is I want to start from this classic paper of the tropical tropopause, I believe is Eleanor's, her first name's dissertation with Brian Hoskins, and it's such a classic, everybody references it. I cut a small section to talk about what is a laboratory tropopause. If you're interested in reading what the definition is, you can do it. But most importantly, I want to highlight this point made there. It says, however, as these authors suggest, the level is rather arbitrarily defined for operational use and has limited physical relevance. Certainly, there seems to be little direct connection between the convective process and the laboratory definition. Okay, I want to mark this for you, and continuing by saying, after that, this paper after paper after paper say that laboratory tropopause is not physical, it's irrelevant, and the cold point is more important. If I cite the names, and many people you know, including, not just many people you know, okay. And the strongest argument for CPT to be important is because the temperature at the tropopause in the tropics controls the water vapor, the amount of water vapor into the stratosphere. Okay. However, this paper did recognize that the cold point is only a reliable tropopause definition when the lower stratosphere is not close to being isothermal, i.e. within the deep tropics. So that's one of the work I did start coming in. That is, when we say CPT as a tropopause destination only work in the deep tropics, where is deep tropics? Okay, do we know how to find it? Okay, so this is just a temperature cross-section composed from GPS data on a particular day along a particular longitude. So I use this as a point, just to make a point, that the CPT and LRT are very interestingly different. So that's your latitudinal behavior of CPT. This is your latitudinal behavior of LRT. So in the deep tropics, there's region they're closely related. Then they quickly depart. I don't know, this pointer is not great. So they quickly depart and become very different. And in this specific case, the tropics as defined by the jet stream, as you see the wind field contour, and it's very wide. But this is not always the case. So there is a climatology using radiosonde, zonal mean, global mean climatology made by Diane Sedell, 2001, shows that in the deep near equator, LRT and CPT is different on average about a half kilometer. Then that increases with latitude. Okay. So one of the earlier work I did, or Lee Manchak was here, we did it together, is to use GPS, global GPS data to see the spatial distribution of the LRT and the CPT. So this is, I wonder if anybody has any better pointer, otherwise I'll be maybe tempted to walk there. Okay. So you can see a large spatial distribution of their separation. If I use seasonal average, this is the DJF season. So you have a region, there's a little of no separation. That is a CPT minus LRT on average near zero. And there's a region you have fairly significant separation on average to be 1 kilometer. Then you have large. So when we say tropics, it's everywhere between the two jets. We use that as tropic. So then this is what we call the shape of the tropics. So tropics actually has a shape, and the deep tropics has a very strong shape. And this, so this is the region, ATTREX did the experiment, Western Pacific phase, that has in the region of almost no separation on the seasonal scale. So in this paper, we concluded the strong influence of the actual tropical dynamics showed up as this large seasonal average that's almost stationary, in a seasonal scale, stationary separation between CPT and LRT. As you know, the CPT bend over and increase to the height, and the LRT. And we know when that happens, CPT has very little meaning about dehydration or anything, because the air motion is more horizontal. The air mass does not really pass that cold CPT. So the region dominated by tropical upwelling dynamics typically showed up as little of no separation. Then we show there's a very large seasonal change in the separation. That is strong indication of the LRT and the CPT are controlled by different mechanisms. They're not really the same thing. Okay. So I want to translate into the question of water vapor. So all of this, a lot of motivated by water vapor in the stratosphere. How is that connected, right? So again, it started from the very early, the oldest history of water vapor. A lot of the stuff motivated by this early paper called a stratospheric fountain. So the paper really is saying, based on some observations over Brazil, deep in the stratosphere, the amount of water vapor there is so little compared to, oh, I'm sorry.
Feel free to answer.
So the amount of water vapor there is much lower than what the local tropopause saturation will produce. So therefore, the author put in the hypothesis that the stratosphere water really is because air preferentially enters the stratosphere through the colder region, like Western Pacific. Okay. So one thing leads to another, that people found out that's not true, that Western Pacific doesn't have stronger upwelling speed, or, there are many reasons to think that's not true. So people start to think about an alternative hypothesis. So one of the early one I found in this paper from Dennis Harman, James Houghton, and Cheng Fu. This paper is very famous for this figure, for how the cirrus cloud is heating or cooling the tropopause region, depending on whether there's the thick envelope cloud under. So it's very famous for that reason. But actually, it says in this paper, proposed this cold trap hypothesis for dehydration, and saying that the stratospheric dehydration mechanism envisioned here is thus one of the cycling water of air horizontally through the cold region, and then go to other places to ascend into stratosphere. This is based on the initial original space observation that the tropopause level cirrus cloud can extend as large extent as 1,000 kilometers. So those large spatial extension cannot be explained by vertical convection because they don't come in 1,000 kilometer scale. So it has to be the horizontal motion. Okay, so that is being tested and quantitatively estimated from this following paper. That's the famous Houghton-Gettman paper. A lot of people followed on later. So this two paper was one of the initial ones to argue for horizontal transport dictated stratosphere water and or dehydration mechanism. So these concepts later on is being investigated through trajectory calculation again and again and again. Many papers. I can't list all of them, but these are two of them. So they all bring up this point called a Lagrangian code point. That is, when you use trajectory calculation, you can find out where the coded point is along the trajectory as the air enters stratosphere. So those called Lagrangian code point. Then you find out the density distribution and the amount, how cold it is. So all of them very similarly point out that the Western Pacific region is the decisive region for water vapor in the stratosphere, just because the large density and the code is the code LCP, the code point tropopause. Okay. So now that we trajectory model has shown and then produced water vapor behavior roughly similar to stratosphere water vapor, in principle, we can just all be happy and go home. But there's still a problem. So one of the problems is when we look at the global models, this is a CCMI models, the work led by Andrew during the first CCMI, right? Then this is the CMIPS 5 models. All the global models, this is a seasonal variation of multiple models, cold point temperature, zonal mean, cold point temperature. They have about 10K spread. So they're very uncertain. That's the other hand. So, so why is it so uncertain? Why can't a global model get it right? So if a global model doesn't get a temperature right, it will not get a stratosphere water vapor right, and which is the case, right? So Doug is in this room, so he said this, which is the case. So one of the reasons potentially is the smaller scale process that the global model cannot represent yet. Okay, so one of the smaller scale process is the gravity wave or wave-driven temperature variation. This is a GPS data-based analysis. Bill wrote this paper, and so you can see the tropopause temperature can have a lot of structures. So if we say this is the coldest one because the wave perturbation enhanced the cold point. And in this case, the wave perturbation created structure. So we can say, in this case, this cold point is both LRT and a CPT, but in this case, the first lapse-rate tropopause will not be coldest cold point, therefore they're separated, right? So later on, this 2015 paper, Kim and Alexander, that's Jiyun Kim and John Alexander that we all know come to our group meeting all the time in the past. So this is using radio sound data, very nicely analyzed when you have a mean tropopause, a cold point, how the wave of different time scales perturb and produce these structures. Okay, in this process, lowers the mean tropopause cold point temperature. So this is another figure from the same paper I showed earlier. We highlighted how the wave process perturb the cold point. There's warm phase, the cold phase, and the mean separation is very small, but the instantaneous separation is very large. These are the points I want to follow on in the data analysis. Now I finally get to the ATTREX experiment. And I think most people in the room know this as the Earth Venture suborbital phase 1, and Eric Jensen, the PI, and this is a very a comprehensive overview if you want to see more about this. So over the 3 different flight years, these are the flight tracks and the flight strategy to do vertically, using Global Hawk, vertically go through the code layer. So that's a critical piece of being able to do this analysis is the flight strategy and the location of the flight. So my analysis focusing on the 2014 ATTREX, which is the Western Pacific phase. So there are 6 research flights, not including the transit flight. So it's pointed here. And we also used these National Weather Service station, radio sound station, to help, and the GPS, all the little dots in here is the GPS profile during the flight season, and to help us to see the vertical structure. So this highlights the temperature, background shading, highlights the flight was done in the coldest region. That's the global lowest coldest place. And the flight vertically transit this layer of the coldest layer. Okay. So the questions, and now that after 10 years of this TTL and the dehydration hypothesis, now we have experimental result to potentially address some of the hypotheses, right? So I will start with the 2 definitions and the TTL. So I say tail of the 2 tropopause. So really just to say, what's the role, based on the data, what's the role of each definition? Is there anything meaningful as a tropopause? Because when people start, if you read the new TTL papers or any tropopause temperature papers, they're just full of contradictory statement. They will say, oh, as we know, the tropical tropopause has no meaning because it's a TTL. Then they say, oh, here is the tropopause temperature. So they're just full of this kind of discussion. So I want to, in this paper, just clearly say, what is the physical boundary from troposphere stratosphere in the tropics? Is there such a physical boundary at all? Okay. Then if there is, which definition better identifies it? So the tropopause is not such a thing that we want to choose whatever we want. It's really, if there is a physical boundary that exists, any definition really just attempt to effectively find it and identify it. So there is a right one. So that's the chemist questions is right. Then the roles, respective roles. Then the observational evidence for this horizontal transport-driven dehydration. So this slide is a little philosophical. That is, when we do these airborne data analysis, so how do you use this, very kind of sporadic and flight data to answer large-scale questions and the fundamental questions? What's the role in understanding fundamental physical processes, right? So very often I see this over and over again. I also have people telling me you cannot do an airborne data analysis without model. Okay, you really have to have model. So the common tendency is to either interpret model to observation in space and time, try to compare, or try to average observations to the model grid to compare. Okay, so my strategy, however, is to encourage to use a conceptual model before going to numerical model. Okay, so if you have a conceptual model, so what is that you're trying to characterize? Even if you use numerical model, you have better chance to do the comparison. So it allow you to do comparison to see what's the right behavior, rather to make 2 things totally different to come up with the same number. Okay, so in this case, my focus. Oh, I'm really sorry. My battery fainted to this small. My strategy is to use the information from tracer distribution and correlations, and to use trace gas relative to physical boundary to identify discontinuity. So, and I stay with the data alone, let the data tell their story before we make a model come in to mess things up. Sorry, I'm just saying that to him. So anyway, this is now the flight. So this is the first example. And you can see in every research flight, the flight track like this. You have a lot of up and downs. And because at the beginning, the ceiling of the aircraft is not high enough, very often at the beginning, we miss the cold point. So these are the radio sound and the GPS pointed where the cold point is at. Only that later half of the flight, we have the cold point. And this is the map of the tropopause temperature, where the flight is and where this profile we're focusing on is this red profile. Okay. So now this is the actual profile, and the black is the temperature, and the green is the water vapor, and the light green is the saturation water vapor mixing ratio based on the temperature profile. And in this case, we have both CPT and LRT lined up in this at this cold point. So they're aligned together. There's no separation. And I'm not sure if it's clear enough to see. This light blue is a layer of cloud right under. So you can see the alignment, the lined up of the saturation vapor ratio and observe the water vapor to show that the layer is saturated. So the measurement is in the saturated region. And the right lower panel shows the ozone water vapor relationship for this flight, for this profile. So as many of you have seen this, if you haven't, that is in the stratosphere troposphere transition region, if you look at these two tracers, one stratosphere tracer, one troposphere tracer, you'll see L-shaped relationship. This L-shaped relationship is a unique signature to tell you where the stratosphere start, where the troposphere end. It's the vertical mixing of the troposphere made this lower branch. The vertical mixing made that happen, and so on and so forth. So this is just an example for you to really want to see this next slide. In this next slide, we have the example 2. This example is an example of large separation between the stratosphere and the troposphere. So you can see the temperature profile shows a much colder cold point above this lapse rate. Okay. Then the water vapor profile, on the other hand, clearly shows dehydration did not happen as a vertical ascent motion, upwelling motion, because the water vapor here is much lower than this temperature will saturate the tool. Okay. And there's some cloud, but it's below. It didn't align with the. So then the key point is, you can see in this L-shaped relationship, the lapse rate tropopause clearly marks the transition from the stratosphere to troposphere. The cold point is just part of the stratosphere branch. It's already in the stratosphere. And there's some details. If you look at the details, that is how the water vapor is lowest at the cold point, the blue dots, and afterward it becomes slightly higher. That is because we're in the northern winter season where the temperature there is the coldest, and the background in the stratosphere is a higher amount of water vapor from previous warm season. So that's part of the reason is that. Okay. Then if we come back to see the map, you will see this particular flight is downwind from a much colder region. That support why this water vapor profile is not a local upwelling, but it's downwind from a colder region. So this is one case. So if we look at everything statistically, this is all the profiles we can have that had both lapse rate and cold point. And we see this density plot that is relative frequency of where we had samples, and it also show this L shape. Then you see this reds are all the LRTs, and the blues all the CPTs, and they have large overlap, but nevertheless, the LRT tend to stay in the corner, and the CPT tend to have climbs up to the stratosphere branch. Okay, so this also shows the two little histograms shows, although on average in this region, LRT and the CPT has very little separation. They're very close to each other. But just like the gravity wave example we have seen, if you look at the individual cases, they actually can separate as large as 2 kilometers. So this is the distance, the altitude distance of LRT, and a lot of them are aligned, they're really the same, but when they separate, they can be quite large. And the water vapor distribution is definitely has a lower, and the LRT has higher water vapor than CPT. CPT has a lower water vapor. So cold point does serve as the limit of dehydration. Okay. So because that figure is very qualitative, so we did some more quantitative analysis. When you separate the layers into blue is above CPT. So this is water vapor, this is ozone, this is the potential temperature. So if you look at the blue, and above the CPT, you have much less water vapor. And below the LRT, the red, you have much more water vapor. That shows you the separation between stratosphere and troposphere. And you have very little ozone below the LRT, and a lot more ozone above the CPT. And the layer in between is showed up in gray. So overall, I would say, although there are some overlaps, the transition, the layer between LRT and CPT would be much more consistent with the distribution of the stratosphere. So it has low water vapor and a lot of ozone. Okay. So the transition is more shown in the potential temperature, which we call the dynamic tracer, because you have very little potential temperature in the troposphere, and the potential temperature is much higher and spread out in the stratosphere. And this is characteristic of the troposphere. This is, so we know the average potential temperature of the cold point is 375 K. So you see this transition. This next figure, I will not spend a lot of time on, just to touch on the point. The point is, way back when Andrew wrote this paper, and Gettleman and Foster, a 2002 paper, explains the TTL can be defined upper boundary and lower boundary as the minimum lapse rate and the cold point. And then later on, more than a dozen years later, I used trace gas tracer correlation to support this. Really is, if you look at the mixing characteristic, this is really true. But the main point here is, from the tracer relationship, in the past, we have already known the CPT actually marks the upper boundary of the transition layer. So that's why to say the gray layer looks like a transition layer between the troposphere and the stratosphere. So that's part of consistent statement with the analysis in the past. So now I want to transition into the next part. That is, now we say tracer marks the, LRT actually marks the top of the convection, and it's not just had no relationship with the convection as people trying to say in the past. And that the CPT marks the top of the TTL. And that it's really a so what statement. So what? So what can we learn with this knowledge, right? How does it help us? And what insight can we gain using this about the composition, that is, and the transport? So that move into the next part is a focus on dehydration and water vapor. So in here, I started by looking at the water vapor in relative humidity space that is connecting the water vapor to the temperature behavior. So I want people to first get used to looking at this histogram in 2 dimensions. That is, we call the relative frequency plot. So this color shading is the percent relative to, is a sampling density in each bins. So the density is scaled by the highest bin for each layer. So they're layer relative frequency. So in this case, this layer, just regular altitude, then we have the mean, for all the 2014 data, we have the mean CPT and LRT. This, if you just look at the regular altitude space, this is what you would see. So then I want to move on relative to physical boundary. So the very first one is if we resort that data, that I put it as a small reference plot there. If we resort this data in altitude relative to left rate tropopause, what would it look like? So right away you can see this density plot become much more organized. And you see below the LRT, your density largely clustered around 100% relative humidity, okay? And then above this point, you have a sharp discontinuity. This discontinuity is close enough to be the 0th order. That shows that this is a physical boundary. You know, I talked about this in the Mines UTS workshop. Ted Sharper's asking me, so you don't mean there's something physical stop them from mixing. So the idea is you have convective driven. That is what your sign is. This is mostly convectively dehydrated because they're near 100% relative humidity. Then when convection run out of steam, so no longer have ways to influence anything above, and something else take over. So therefore, the mechanism controls the discontinuity is remote, but the effect showed up locally as a sharp discontinuity between, you can absolutely tell there are 2 spheres, 2 layers. This is a layer, that's another layer. They're not the same, okay. So then I go to next coordinate, is the cold point relative coordinate. And interestingly, in that space, you will see a very different behavior. Okay, you do see that discontinuity at the cold point, but you also see something else. So these 2 branches I call 2 modes below the cold point. This one I call the locally dehydrated, the local dehydration mode. And there's another one I call the remote dehydration mode. That is, the reason the relative humidity here is so low is because it was not controlled by the temperature locally. You know, the temperature locally controlled water vapor is 100% relative humidity, okay? Of course, plus minus, you have supersaturation and so on and so forth. But if I focus on the densest distribution, so this is convectively controlled by local vertically controlled, and this is not. So this remote mode is what we think.
Can I ask a question?
Sure.
It makes sense to me, but I'm curious why you expect a distinct branch there for the remote dehydration. Why wouldn't it just be continuum? You have a range of colder temperatures upstream.
Yeah, so.
It's very distinct, which seems a bit surprising.
Right, so I show that as the LCP, the local, the Lagrangian cold point. So only the coldest region that contribute to that. So in this case, it's whatever upstream. There's a cold region upstream. So if you have a sweeter distribution, it doesn't always show up, only the coldest one. Doesn't make sense. So that showed up as a branch. Yeah. So, so I want to look at more in this cold point and relative mode, different mode, the local mode and remote mode. So to further answer these questions. So this very first one, I call it the evidence of remote dehydration dominating the stratosphere water vapor. So it's a very bold statement. I want to see how well that works. If it is not working, I'm sure Eric will tell me. Okay. So So I want to see things first in two layers. The cyan layer is 1 kilometer above the cold point, and the dark blue layer is 1 kilometer below. So first we're looking at a water vapor distribution. You can see this is the lower stratosphere layer, this is the upper troposphere layer. They have a different distribution. But when you look at the three boxes, the light green is the stratosphere box, the red is the remote dehydration mode, the blue is the local dehydration. So their water vapor showed up in the lower panel. So that, in my mind, kind of says the remote dehydration has the same distribution as the lower stratosphere, the box above distribution. Shows how important, how significant the role of that remote dehydration is.
For this data set.
For this finite measurement, yes. So then this go on to the Lagrangian cold point, okay. So same three boxes, and now you got used to it. So the top panel of the histogram shows the temperature at the time of the measurement in the three boxes. And the bottom shows the temperature at the dew point, that is the temperature corresponding to the water vapor. So that is the temperature at which that water vapor formed, that dehydration happened for that water vapor to be set that value. So that's the dew point. So you can see we have the green box, what I wanted to focus on. No, the red box, the red histograms. You can see the red histograms are the samples measured at a relatively warm place. Their temperature is much higher than the blue. That's the local. So, but when you look at their dew point, the dew point temperature of this remote dehydration look very much like the box above. So that kind of says, you know, they have similar dew point as what we end up having in the lower stratosphere. I guess I went back to this same thing. That's the cyan is lower stratosphere layer, so that how much is similar to the green and the red layer. Those are the point I called Lagrangian cold point, because they are the temperature that set what the water vapor are, that water vapor values are. So this is the pretty much the last figure. Is again, it's the potential temperature. Is in some ways can be a little unfamiliar to a lot of people. That's, we look at these two boxes, the red and the blue. They are in the same relative altitude to the cold point. But if you look at their potential temperature, the red and the blue are very, very different. And the red box, that is the remote box, look much more similar. The range of potential temperature they have covered are very similar to one layer, the layer 1 kilometer above the cold point. So all that really is saying, this is the layer, the remote box, the remote dehydration happened at a higher potential temperature and very close to the tropopause. And in other words, they happened above the convective influence. So, yeah, so if that makes sense, that's what the information is. And I can further go on to estimate the potential temperature lapse rate that they're indicating. That indicated they're in the region much more stable. They're not in the region of unstable that's vertically mixed and or convectively influenced. So maybe a more intuitive way is to show we had 3 flights much more in the cold region itself. So when we look at the samples, these 3 flights contributed more to local dehydration. Then we had 3 flights had a much more warmer temperature influence and a downwind from the colder region. So in the tropic, this is the anticyclonic flow, as you see. And the wind field arrows are very small, so I emphasize that by larger arrows. So all these arrows really is indicating how the flights in this one is in the cold region, the flight in this one is downwind from the cold region. And so is the other one. I didn't draw additional arrow. So from this analysis, I want to draw the following key points. So the first one is that the measurement in relative coordinate space has shown that there is a well-defined physical boundary at the tropical tropopause. And this physical boundary is better defined by the LRT. And then the role of CPT, there is a role of CPT, and the data show that the further dehydration occur in this layer between LRT and CPT. Then the tracer relationship, the water vapor and temperature relationship indicates that the layer between the LRT and the CPT is dominated by horizontal transport. That is, we see the remote dehydration, they don't really show up in the lapse rate relative coordinate. They're above the lapse rate and below the cold point. So they're really, if you think about lapse rate, really is an indication of convective influence. So they showed up above the convective influence. So this we said again is this points between LRT and the CPT indicates that that's part of the TTL, part of the transition layer into stratosphere. The second set is really is following up on the remote dehydration. The remote dehydration mode much more consistent with the stratosphere water vapor distribution itself is evidence how important is the Lagrangian cold point rather than local cold point. So this is the global hawk, as those of us involved in the experiment knew how at the time the difficulty was as an experiment to study TTL, supposed to fly in the coldest region of the atmosphere, and only in the later stage realized there's a limit of temperature at which the fuel will freeze. So that limit is higher than the temperature we want to fly. So at the time of the flight, it was some difficulty as to say that where we can fly, how long we can stay in the cold region, and Eric Jensen probably lost some hair over that. But it turns out that because we flew in the downwind of the cold region, and we did not really miss the dehydration because of the fuel limit. And this point is about the wave perturbation. So we have seen many works, so a lot of paper talking about how important gravity wave is because the perturbation will decrease the cold point temperature, will decrease the average cold point temperature, therefore it's very important for water vapor, for dehydration. And this work, I want to challenge the idea how much the cold point perturbation by wave is dominating the process versus large-scale transport. So if the horizontal transport from colder region is the dominant process, and although the wave perturbation is still important, it's not the wave perturbation at every cold point that contributed to the dehydration. So I want to challenge I think there needed to be some additional thought process on smaller scale process versus large scale process. So the last set of points, again, is a little philosophical. That is to start from the beginning, we think integrating dynamic information, the structural dynamics, thermodynamics, is important information for understanding the contribution, the composition. So how the dynamics, microphysics, and the transport all together and the chemistry control the composition. And the statement, more importantly, I want to also say is the other way around. I think the trace gas measurement, the trace gas distribution, really has a unique angle and can provide a unique set of information to inform the complex region, how the multi-scale interactions is really doing to the atmosphere. Because the composition, if you do it right, really tell you what the dynamic has done, the multi-scale process has done in this region of high climate sensitivity. So with that, I will capture the beginning that is, chemistry and chemical composition can indeed also inform the dynamics and on things or two. Yeah. Okay. Thanks.
You could go back to your first set of key points. Number 2 there, you're saying that the data show there's further dehydration between the LRT and the CPT. Actually, when I looked at your plots, there doesn't seem to be clear evidence of that, at least not statistically. Mm-hmm. Your PDFs of water in the middle region and the above region look very similar. If you want to, it's a lot of slides back, but.
Yeah. Yeah, that's the statement there I didn't quite complete. So that on average is very small. Yeah. It's less than half ppm MV, so it's relatively small.
Half's pretty significant. It looked less than that to me in the plot, but anyway.
Yeah. So overall, I think really the horizontal flow driven is dictating everything. So this additional amount. The fact that the cold point is still colder is a smaller. Yeah, I agree that I have to.
So you kind of mentioned at the end the role of microphysics, but you didn't really talk about it. I mean, one of the roles of waves is it kind of changes how the microphysics is going to operate with the dehydration, mm-hmm. right? Because you have ice nucleation processes that are not at 100% relative humidity. Mm-hmm. And I'm wondering if you've thought about that at all and how that would play into, either setting offsets or.
So are you alluding that there's a cloud?
Don't understand microphysics.
Agreed. So you need you need a third person in your discussion, which is the cloud microphysicist.
So I actually had this as my actual slide, one of the almost only actual slide. So it's a really good question. If I had another half hour, I would invite everybody to discuss it. So there is this, how this cold point. This is this ATTREX mission as well. So in the middle is the cloud LiDAR. But because when you have LiDAR, you're doing horizontal flight, right? Is that how Eric can straighten me? Yeah. So then you start to up and down. So before and after, you see this true temperature profile. So it's in situ, remote sensing in situ. That's what you're seeing. Okay. So the fact that the cold point, because the wave perturbation, the cold point is cold, seem to be associated with additional dehydration from cirrus cloud formation is part of the point. So on the other hand, I want to throw out this very provocative statement. So would it be also possible, because the scale of the cloud is so large, that horizontal transport mixed, form to warm air flow through the cold region and left this layer, not only left this layer of cloud, also mixed in colder air to form the temperature structure. So anyway, so these are the questions I had hoped to talk to Joan Alexander, but she hasn't been around. So Andrew, it may not be really toward your question, so if you want to, I'm just saying that the cloud is part of the deal. Yeah.
Laura, that was a very nice talk. I really enjoyed this. One question I had, almost following up to Eric, with this, what's happening between the lapse rate tropopause and the cold point tropopause, where there's not much dehydration. I probably agree with you. Where that showed up nicely was in your ozone, water vapor ozone correlation plot, where really your lapse rate was the corner, and then it went up quite drastically as you go up into the stratosphere. My point I was trying to make here is that ozone is actually a really, really valuable tracer to look at that, much better than temperature in our age, because the ozone doesn't care about the temperature. Whatever the dynamics does, the ozone just goes with it, at least on those time scales as an inert tracer. And I wonder if you looked a little bit more using ozone as your reference rather than temperature or our age.
In the tropics, ozone started to change at the top of the convection. So it's more at the level of minimum stability. So we looked at the discontinuity at the cold point and the lapse rate. There is a small one, it's not a drastic one. So because it's a unique characteristics, so there is a horizontal mixing from the sideways to increase the ozone in this level. There is also, other argument. So, but in terms of using ozone as a tracer for boundary for the tropopause, in this case, it's not as effective, in my opinion.
I mean, typically, I think when you talk about this transport from colder regions, I mean, that's probably transport scale of, I don't know, days.
Mm-hmm.
And I would guess ozone doesn't care on time scales of days.
Mm-hmm.
Probably more like weeks or longer than that.
Yeah, but the colder region definitely will bring down the water vapor, will unlikely have a strong gradient in terms of its ozone. But I will look into it. Yeah, that's what my thoughts are. Yeah.
You talked a lot about dehydration. What role is left for convective moistening or overshooting? Is that pretty much not considered important?
So Eric, you want to answer that one?
Huh? Convective overshooting, hydration by convective overshooting. It happens. There's anecdotal evidence that it happens, but it's very difficult to evaluate how it affects the global budgets. The best estimates, I think, suggest it's pretty negligible. But that's an opinion. Other people disagree with me.
So right now in the stratoclim community, because they are in the region of active deep convection, so they are looking into lofted ice, and Martina's here, and she has all the water vapor and ice information. But again, on global scale.
Mm-hmm. Thank you.
Yeah.
Thanks, Doug.
Yeah.
On this one, you might actually be right.
Yeah. Yeah.
Actually, I have a comment to that one. He's loud.
It's okay. We weren't
Not loud
trying to be
enough
too
to be
serious
heard on
about
the
this
internet.
recording. Yeah.
With the convective hydration of the stratosphere, probably in the tropics, I fully agree. I mean, the lapse rate is so strong above the cold point, very little convection makes it in there. But in the mid latitudes, it might look quite differently.
Certainly over the North American monsoon.
Yep.
Yeah. But in the lowermost stratosphere.
Exactly.
Yeah.
So I mean, it doesn't play a role. It depends on where.
Yeah.
Any more questions? Let's thank Laura again.
Thank you.